All right, so this is the last module of this course, ECE 5550. So this module is going to talk about field effect transistors. So field effect transistors are also called MOSFETs. And this is by far the most important device out of all of the solid state devices that we look at. So in this section, we are going to be covering the second of the three major devices. The first major device is diodes. Second of the major devices is the field effect transistor, and the third is the bipolar junction transistor. So bipolar junction transistors we're not covering this semester because we've put more emphasis on diodes, MOSFETs, and some of the more fundamental level things. Bipolar junction transistors, by the way, are used in some high-speed electronics, some analog circuits, but the MOSFETs are really more important given the importance of digital switching and computation. And even some of the analog functions that used to be done on bipolar junction transistors are currently done on MOSFETs. So the MOSFET is the most widely used type of field effect transistor. Some of the less often used devices is the MOSFET, the HEMT, the heterojunction devices, the junction field effect transistors. They are a little bit less frequently used. So we're not going to be looking at them in this class. Professor Gosde teaches a course on nanoelectronics where some of those other devices may be covered. So in terms of conceptually, like what you're going to be learning in this module, the MOSFET is a new concept. It builds on some of the ideas of metal semiconductor junctions and also some of the fundamentals ideas that we've covered in chapters 3, 4, and 5. So, but fundamentally, the field effect idea is a new concept. That's something we haven't not covered before. So there's going to be a combination of concepts that build up from what you've already learned, and then there's going to be some new concepts thrown in. Okay. So I like to start with motivating why MOSFETs are so important. I read something I think last year or so that said the MOSFET is by far the most manufactured device by humankind. Okay, so think about all the devices and contraptions and widgets that we've made over the last 100,000 years. The MOSFETs are by far the most manufactured device. And why is that? Each computer chip that we make has 2.1 billion transistors nowadays. A typical GPU that's used in data centers for doing facial recognition, natural language processing, and other AI type functions, and even gaming. These types of computer chips have more than 20 billion transistors. And remember, just to give you like a sense for scale here, the world population, I think, is what, like in the I think it's something like 4 or 5 billion, and the world capacity is maybe 9 billion. So each one of these chips has well more transistors than the world population. Okay. 99.9% of all transistors are MOSFETs. So that's why MOSFETs are a big deal. So they're used primarily in two applications. One is digital switching, and the second is analog amplification. And you can already see that these two things are the most important things when it comes to wireless devices and digital computation. So let's just talk a little bit about those two things. So the first thing is, if you're trying to make a computer, you need to create something called a digital switch. A switch is something where you can, when you turn the switch on, just think about a light switch. You turn the light switch on, it allows current to pass through. You turn the switch off, it doesn't allow current to pass through. Okay, the difference between a MOSFET and a regular switch is that the MOSFET is electronically controlled. If you think about a regular switch, whether the switch is on or off, I'm speaking in really obvious terms here, whether the switch is on or off depends on the position of the switch, and you mechanically toggle the switch to the on or off position. Okay, that's a slow process, right? So if you're trying to make a computer out of mechanical switches, it's going to be a very slow device. The transistor is an electronically controlled switch. Imagine a switch where you could, by applying a certain voltage, you could get the switch to turn on. And by removing that voltage, you could get the switch to turn off. Okay, the voltage is applied to a terminal called the gate. Okay, so if you can electronically turn a switch on and off, and you can do it, you can switch it on and off very, very fast. And that idea is the basic building block of microprocessors. If you take a course in computer architecture or digital design, you'll see why a switch, how a switch can be used as a basic building block for making things like logic gates, AND gates, OR gates, how you can make memory cells out of them, like NOR memory or flash memory and things like that. Okay, so that is a key capability that MOSFETs provide, and they do a pretty darn good job of it. You can make switches out of things like bipolar junction transistors as well, but they are less energy efficient and they're slightly more complex to build. The second important thing, given the fact that everything we own nowadays is wireless or has some kind of Bluetooth or Wi-Fi on it, is analog amplification. MOSFETs can actually be used in amplifiers. So we have a combination of electrical engineers and material scientists in this course, and chemical engineers. So for the electrical engineers, the MOSFETs can be used in the common source amplifier. They can be used to make current sources. Those are, and they can be, combined in many different ways to make differential amplifiers and so on and so forth. So amplifiers are extremely important for radio communication because we have these radio signals coming from the cell phone towers. We have these radio signals coming from our Wi-Fi routers and mesh routers. And a lot of times those signals can be fairly weak. They're picked up by an antenna. And there's a weak voltage on there, and that voltage has to be amplified to a larger voltage. Okay. And again, like with amplification, bipolar junction transistors were used pretty frequently for doing amplification before that. And even before that, the vacuum tubes, these light bulbs looking devices with vacuum inside, was used for amplification. I won't get into the details of that. Obviously, when transistors started to be used, the size of a radio went from the big boom boxes that you see in the 1980s to like the tiny transistor radios that you see, to the point where nowadays you have all these functions in your cell phones. But from a big advance happened in the early 2000s. And that's when bipolar junction transistors, which were used a lot for amplification, they started to be replaced by MOSFETs. This is because analog designers came up with ways to use MOSFETs, which traditionally weren't the greatest devices for analog amplification. They were these, the circuits were designed properly. The devices were optimized so that you could amplify signals that in the 2.4 gigahertz range, which for Wi-Fi and Bluetooth. And when that happened, there was a transition point. If you look kind of back in history, like that transition point happened sometime in the early 2000s, where these suddenly the MOSFETs devices, and CMOS in particular, could be used for analog amplification. The same technology that was used for digital switching up here, the same technology that was used for computation and microprocessors, could also be used to do analog amplification. That was huge because now in one manufacturing process, you could make the wireless components for amplification components, and you could make the computational part of it. So after that kind of turning point in the early 2000s, we just started to have Wi-Fi, Bluetooth, all these wireless functions became ubiquitous in all devices. Before, the wireless portions used to be separate components, and so there was more expensive. So nowadays, that integration, that level of integration is super important about why MOSFETs have become so prevalent. So the ability of MOSFETs to perform both of these functions is very important. So here you see the Intel Skylake processor. This is your typical multi-core microprocessor with several billion transistors. The GPU I mentioned has over 20 billion transistors for doing parallel computations. And over on the right side, I showed a picture of this back in the first day of class. This is the Michigan micromote. It's designed at the University of Michigan. This is where you go, you have chips that are very, very, very small. You can see this on the edge of a dime here, or edge of a nickel, I think. And these tiny chips have fewer transistors on them, maybe just hundreds of thousands of them, but they have wireless functions built into it. So these chips can be made very, very small. And so that's why they're called micromotes. This is actually a sensing device. It has sensing, computational, and wireless components in it. Pretty amazing. We've talked about Moore's law. I think this is just a slide that sort of shows the progression of the microprocessors from 1971 to the 2000s. And of course, that trend has kind of continued, but started to level off today. So let me just sort of leveled off like this. Let me just remind everyone what Moore's law is. Back in the 1970s, the founder of Intel predicted that they would be able to pack more and more transistors on a chip. And by packing more and more transistors on a chip, they would be able to do two things. One is that you'd be able to do more complex computation, right? Because the more transistors you have, the more compute power you have, because these transistors are used to perform arithmetic logic and things like that. So more transistors means more computational power. The second thing, the second advantage, is that by making the transistors smaller, they actually operate faster. So you could switch the transistors on and off at a faster speed. That translates into the clock speed of your PC or your cell phone or what have you. So back in the 1970s, there were 2,300 transistors on a chip operating at 108 kilohertz clock speed. And that was when the transistors were 10 microns in size. Remember, your human hair, the diameter of a human hair is 100 microns. So this is 1/10 of that. That was back in the 1970s, that the transistors were still pretty darn small. Okay. And then I mentioned that you can make memory cells out of transistors. So given that you only had 2,300 transistors on a chip, the amount of memory that you could have on there is 640 bytes. Yes, bytes, not megabytes, not gigabytes, bytes. So it's a pretty small amount of memory. Okay. And of course, there were no hard drives in the computers back then. Okay. By the 2000s, there were already 40 million transistors on a chip. The Pentium 4 processor was 40 million transistors operating at 1.8 gigahertz clock speed. So we went from hundreds of kilohertz, which is 10 to the power of 5, to 1.8 gigahertz, which is 10 to the power of 9. Okay, 4 orders of magnitude increase in clock speed. And we went from 2,300 transistors per chip. So this is 2.3 times 10 to the third to 40 million. That's 10 to the power of 7. And now we are close to 20 billion, which is 3 orders of magnitude beyond this. Again, a huge increase in the number of transistors on the chip. And we've done that largely by shrinking the transistor, gone from 10 micron transistors, which is already very small, down to 0.18 micron transistors in the 2000s, 180 nanometers. And now we are at an incredible, like 15 nanometers or so, 15 nanometers. So just the gates of these transistors are just a few atomic layers thick now. It's just quite incredible. Memory sizes have gone from 640 bytes of RAM to 4 gigabytes of RAM in the 2000s, and now a typical PC would have, maybe like 12 to 16 gigabytes of RAM. Okay, And with three-dimensional memories, the amount of storage that you can have, particularly on hard drives, has increased from next to nothing to hundreds of gigabytes. So Moore's law predicted this, that companies like Intel and other manufacturers would just be able to make the transistors smaller and smaller and smaller. And that trend continued on for more than 4 decades. Okay, Moore predicted that the number of transistors would double every 18 months. In reality, and it ended up happening every 24 months. A little bit slower than predicted, but man, look at this. It's quite amazing. Now we've gotten to the point where the transistors have not been able to get smaller and smaller every 18 months, simply because it's really hard nowadays to make transistors smaller when you're already at the 50 nanometer scale. You're getting close to atomic scale, and it's really, really hard to make them smaller beyond that. They have required building new transistor designs out in 2011. And I'll just put, remember, so I know one of the groups is doing a project on the FinFETs. Okay, the FinFET was a new type of transistor design which allowed Moore's law to continue extending. And then in 2021 and beyond, we're starting to see the nano sheet transistors. So these aren't in full production yet, but this is another, like, three-dimensional geometry where you have better control of the gate voltages. So new transistor designs are coming out that to help keep this trend going, but it's becoming very difficult to continue Moore's law in the sense that it had for the last 40 years. These 40 years, okay, was done using basically the same transistor design with some incremental improvements. These were the 2011, 2021 were like fundamental redesigns of the geometries of the transistors. And improving it beyond the 7 or 5 nanometer node is going to prove to be very, very challenging. In terms of importance, I talked about the geopolitical importance of computer chip manufacturing in the first day of class. It is a very competitive market right now. The market to be able to make these transistors very, very tiny. There are major manufacturers in Taiwan, in China, in the US. Some of the specific optical instruments that are used in the lithographic processes used to make these microprocessors are made in Scandinavia. So there's just big competition for, it requires global cooperation, but there's still a lot of competition at the same time. So that's a whole topic for another class. But let's go today into the structure of the MOSFET. Today, we'll talk about the IV characteristics a little bit today, introduce that, and cutoff, triode, and saturation. These are the 3 operating modes of the MOSFET. We will be talking about the physical and energy band models of each of these modes of operation. So we'll talk about the equilibrium mode, accumulation and depletion mode, the inversion mode, which is very important, and then the triode and saturation. These are kind of the operating modes of the MOSFET. And then we'll get into some of the transient and second order characteristics of the MOSFET and some of the scaling issues. What happens to the transistor? How does this performance change when you start making the transistor smaller and smaller? Okay, so I hope that this will set you up for future classes in MOSFETs. This just goes over the basics. Professor Gosde will be teaching another class called nanoelectronics, where you go in depth into some of the newer types of MOSFET designs that are coming out there. But this will give you the fundamentals to do further explorations in this area. So let's stop here for a second. Any questions so far on the material that we've covered thus far? Like why MOSFETs are super important? Why Moore's law? Anything about Moore's law that you may have, questions you may have? Okay, no questions right now? Okay, great. Okay, let's go over the 2 types of MOSFET devices. Okay. Now, there is an NMOS device, and then there's a PMOS device. Both of these devices are made using the same manufacturing process which has another name called CMOS, complementary metal oxide semiconductor. Let me write that down. The two types of MOSFETs in a CMOS process, a manufacturing process. And CMOS is complementary metal oxide complementary metal oxide semiconductor. That's what CMOS is. You probably heard that term CMOS because it turns out that CMOS manufacturing process, which has been developed and optimized over 4 or 5 decades now, it allows you to make both NMOS and PMOS devices, both of these devices in the same manufacturing process. And having both of those turns out to be very important for the two functions of MOSFETs, the digital switching, which is used in logic gates, and also for analog amplification, which is used for wireless radios. So the NMOS and PMOS devices have 3 terminals, a gate, a drain, and a source. So, I mean, just for context here, remember, like, the basic things like a resistor or a capacitor, an inductor, these are all 2-terminal devices. So even a diode, it's a 2-terminal device. There are 2 places where you make electrical contact. The NMOS and PMOS, they have more involved equations because there's 3 operating terminals. So you have to think about how do you operate the device. And so I'll go over that in a second. So the NMOS device, it looks like this. This is the circuit symbol for it. Okay. And you can see that it has like 3 terminals here, the drain, the gate, and the source. And the way to think about this symbol, I like to think about the intuition behind the symbols too. Remember with the diode, I said there's an intuition behind the diode symbol, okay? The way that circuit designers like to think about the diode is that the diode conducts current in one direction. So it conducts current in this direction. It doesn't allow current flow in the opposite direction. So that's why the symbol looks kind of like a triangle that's pointed from left to right. Okay, and this little line here, it kind of represents the fact that current cannot go in the opposite direction. So I want you to see the intuition in the NMOS symbol here as well. So in an NMOS device, there's a gate, a drain, and a source. There's 3 terminals to it. And the intuition I want you to think about here is that the gate controls whether current can flow between the drain and the source. Okay, that'll make sense in just a second. The typical operation of the device is as follows. You're going to apply a voltage to the gate. Okay, so as you apply a voltage to the gate, you remember how I was giving you the analogy of a mechanical switch? This is the circuit diagram for a mechanical switch. Okay. So the switch can be moved into this position, and when it does, it'll form a short circuit between the 2 terminals, and it'll allow current flow. And when it's moved back in the opposite direction, then it'll be open, and it will not allow current flow between the 2 terminals. That's the way I want you to think about a MOSFET. Okay, so in an NMOS device, the current will flow from the drain to the source, okay? So it'll flow in this direction. And that's why the arrow here, it shows the direction of current flow, okay? The current is flowing from drain to source, okay? But you can either turn on the flow or you can turn off the flow. So we call this a channel, This region here is called the channel. You can either allow current flow in the channel, or you can block current flow in the channel. And whether the channel is on or off depends on what gate voltage you put on it. Okay, so this was your mechanical switch up here. You can physically move the switch to the on or off position. In the NMOS device, the gate, the voltage at the gate controls whether this channel is on or off. Okay. All right, so the gate voltage, which is the VGS, the gate to source voltage for the NMOS, or the source to gate voltage for the PMOS, is applied between the gate and the source terminal. So you apply a voltage here, VGS, okay? Now, I know I just said, like, you apply a voltage to the gate, okay? Think about the intuition I would like you to have is that you do apply a voltage to the gate, okay? But remember, voltages have to be applied between two sources. You can't apply just a voltage one terminal. You have to apply it between two terminals. So in an NMOS device, that voltage is applied between the gate and the source. The gate has a positive voltage, and the source has the negative side of the voltage, okay? So the intuition is, if you want this channel to be on, if you want current to be able to flow between the drain and the source, then the VGS, this gate voltage, has to be high enough. We say that it has to be greater than the threshold voltage of the transistor. So when the gate voltage is greater, the VGS is greater than VT, the transistor is on, and it will allow current flow between the drain and the source. Okay, in order to get current to flow between the drain and the source, you also have to apply a drain voltage, right? Even if this channel is open, you don't get current flow through here unless you actually apply a drain to source voltage as well. Okay, so a three-terminal device, you actually have to apply a VGS and a VDS, both. And then you will end up getting a drain current flowing between the drain and the source, okay? So you apply a VGS and you apply a VDS, and the result is you'll get a drain current flowing from here, through the device. Okay? So that's the NMOS device. The PMOS device is kind of what's called the complement of the NMOS device. So you'll see in the PMOS device, the orientation of the source, gate, and drain are flipped. The source is on the top, whereas at the NMOS device, the source was on the bottom. Okay, and you see the arrow flows from the source into the drain. Okay, so notice the arrow is down here for the NMOS device, and it's up here for the PMOS device. So the current still flows, you can think about current flowing from top to bottom, but the source is on the top in a PMOS device. So the current flows from source to drain in a PMOS device, drain to source in an NMOS device. In a PMOS device, the voltage is applied between the source and the gate. So in other words, the gate, you have to apply a negative potential to the gate instead of a positive potential to the gate. In order to turn this device on, the gate voltage actually has to be negative. So it's opposite polarity. And we can talk about more of the physics of how the PMOS device works. We'll talk about that later. In order to get current flow, you have to apply a voltage across the channel. So you have to apply the source to drain voltage. Here you apply a drain to source voltage, VDS. Here you apply a source to drain voltage instead. And then you will get current flow going from here to here. All right, any questions so far? So with the three-terminal device, you have to apply two voltages, and then you get a corresponding current. Whereas with these two-terminal devices that we showed here, you just apply one voltage and you get one current. All right. So let's go over the current voltage characteristic of the diode, or I'm sorry, of the MOSFET. So just focus on what the characteristic is right now. We're going to talk about how that characteristic emerges once we get into the specific discussions on how the physics of the MOSFET work. Okay, So with the NMOS device, again, you have the circuit symbol here, the drain, the gate, and the source. So the way that we think about the IV characteristic, the current voltage characteristic of the diode, is we first apply a VGS, hold the VGS constant, and then we apply a VDS, and we can ramp that VDS, going from low VDS to high VDS, and plot the current, the resulting current, as a function of VDS. Okay, so a typical IV characteristic for an NMOS device with a threshold voltage of, say, 0.8 volts might look something like this. Again, the current is plotted as a function of VDS. Okay, so it will be plotted for several values of VGS to, to account for this parameter. So first of all, when VGS is 0, when VGS is 0, the intuition here is that there's no gate voltage being applied, so this channel is off. Okay, so we can just put an X through here. No current is going to flow in here. Channel is blocked. So the IV characteristic is going to look like this. Okay, so let me just read these points here. Both type of MOSFETs operate in something called the cutoff, triode, or saturation. I'll get into that in a second. It depends on the gate to source voltage, the drain to source voltage, and the threshold voltage. So the threshold voltage is the gate voltage at which the transistor turns on, allowing current to flow between the drain and the source. That's what I just mentioned. So if the gate voltage is not greater than the threshold voltage, well, then your current voltage characteristic is going to be in the cutoff region, and it's going to look something like this. Okay, I don't know if you can see this very well, but the green line looks like this. Okay, for VGS equal to 0 volts. Regardless of what voltage you apply on the drain side of it, this channel is blocked. So it's an open circuit. Well, nothing will flow through there. Okay, so the next curve is when VG is equal to 1 volt. So the threshold voltage for this example is 0.8 volts. That means the gate to source voltage is greater than the threshold voltage. So that means that this channel is now on. So current can flow through this region. Okay, so that's why you can see that the current is non-zero here. Okay. The second thing you'll notice is that initially it looks like the current goes up as a function of the current goes up as a function of the applied voltage. So you see something like this. Just to remind everyone, for a resistor, if you plot the current voltage characteristic for a resistor, it looks like a straight line like this. As you increase the voltage, you increase the current, right? So that's kind of what's happening here. We're increasing the voltage and the current also increases, but just for this portion here. Then it tails off. So you get into a situation where as you increase VDS, then the current, it flatlines. It's just horizontal here. Actually, there's a small slope to it. We'll talk about that a little bit later, but for now, think about it as being kind of horizontal. So just so you can see that there's two different regions of behavior. There's this section here where the current goes up as a function of voltage, and then there's this section here where the current becomes independent of the applied voltage. Okay, so we call this region here, we call that the triode region. The triode region happens when VDS is less than VGS minus VT. Please fix this in your notes. This should be a negative sign here. At small values of VDS, we are in what's called the triode region. The current, just at the beginning of it, the current starts increasing linearly as a function of VT, and then you get this tapering off effect at the end of the triode region. And then the saturation region is out here when you see more of a flat line. Okay. So question for the electrical engineers in the class. Resistor has a current voltage characteristic that looks like an increasing function like this. Okay, so that explains, that can be the behavior in the triode region. What about the behavior in the saturation region? What type of circuit component has a current voltage characteristic that looks like a flat line?
Current source.
Current source, that's right. So in terms of utility, the circuit designer would see this and say, hey, you know, like in the triode region, the transistor can be used as a resistor. If we're clever, we can use this thing as a resistor just in this zone. And then if we need a current source in our circuit, current sources are a very important part of amplifiers, then we would use MOSFETs that are in this region of the curve, and that are in what's called the saturation region. Saturation is when VDS is greater than VGS minus VT. Okay, so there's two uses for these transistors here. All right, so if we continue to plot other curves where, let's say VG is equal to 2 volts, then the curve would look something like this. You'd get more current in the saturation region, and you'd have a slightly higher slope in the triode region. And then VG equals 3 volts, VG equals 4 volts. The shape of the characteristic is very similar. Just the magnitude of the current goes up with the larger gate voltage that you apply. Now, the intuition, the way you can think about that is the more gate voltage you apply, the more you're turning on the switch. Okay, this is where the analogy between a mechanical switch kind of breaks down. You know, the mechanical switch, it's either on and it's a short circuit, conducting current very nicely between the two poles, or the switch is completely off and it's conducting 0. In a transistor, it's not quite like that. In a transistor, you can actually control how much current you can allow to flow between the drain and the source. Okay, so it's kind of like if you're, you know, if you've dealt with like flow control stuff in plumbing or other types of experiments, you can think about this as like kind of a needle valve. You know, like with the needle, you can adjust the position of the needle, and you can adjust the resistance of the flow channel that you have. So that's kind of more how you can think about the gate voltage is more akin to where that needle position is. Okay, so as you apply a larger gate voltage, you can imagine that you're allowing more current to flow. That this little channel region is opening up wider to allow more current flow between the drain and the source. So that's why your curves look like this. It's actually a nonlinear function. That's why you can see that when you jump from 1 volt to 2 volts, you know, there's a certain distance here. When you jump from 2 volts to 3 volts, it's larger. When you jump from 3 volts to 4 volts, it's even larger still. Okay, so it's actually a parabolic relationship. We'll get to that later. Okay, so this is how I'd like you to think about the MOSFET current voltage characteristics and why it's useful to circuit designers. So if we were to actually plot this parabolic curve here, this would actually tell us the transition between the triode region and the saturation region. So we'll get to that later when we derive the relationships between the triode and saturation region. Okay. Any questions? Okay. For a PMOS device, as I said, you can draw an IV characteristic for a PMOS device. It would look like this curve, except it would be reflected over the x-axis and the y-axis. So it would be reflected across the origin, and that's how the current voltage characteristics would look like. Okay, the PMOS is the complement or the inverse of the NMOS device. Okay, so MOSFETs in digital circuits. MOSFETs are the basic building block of digital logic gates and microprocessors. So this is an example of a digital inverter implemented in CMOS. This is an inverter gate. That means that when you put in a digital 1, or let me just say, when you put in, let's say, a 5-volt signal at the input, it'll give you a 0 volt at the output. If you put in a 0 volt at the input, it'll give you a 5 volt at the output. So it inverts the signal that's coming in. And if you look at the inside of a logic gate, you'll see that it's actually made up of a PMOS device and an NMOS device. And so you can kind of see here that this is a supply voltage here, this is ground, and this is your input voltage. So the kind of the intuition of how an inverter works, and you don't need to know this for the exam because this is not a course in circuits, but I want you to know is that, let's say if this voltage were, say, if this voltage were, say, 5 volts, okay, then your VGS is, this VGS is greater than the threshold voltage, and this device is on. So it allows current flow between the drain and the source. Okay, so that means whatever voltage is here will end up being reflected here. So the output is low. So the output is 0 volts, ground. And in the other situation, so let me erase this. If Vin is 0 volts, then it turns out that this one will be off. This one, the PMOS device, is the one that will be on. So because this is kind of like a short circuit here, the output will be VDD, which could be 5 volts, whatever your supply voltage is. This device is off in that case. So the complementary MOS system, CMOS system, the reason it's called complementary is because in typical gates, either the NMOS device is on or the PMOS device is on, and the output voltages are adjusted accordingly by the circuit. Extremely low power, extremely scalable. Okay, so this is what it looks like at the transistor level. At the physical level, this is what a CMOS device looks like. And that's what this course, of course, is focused on. You can see here that you have a P plus substrate, a P minus region here, and I don't know if you can see this very well. You can see that there's a P region, a P-type source and drain here, and then an N-type source and drain here. So this is your PMOS device. This is the NMOS device. Okay, we're going to get into the details of this now. So I just want you to see that this course is more focused on the physical layer, how this circuit that you see here is actually implemented on a physical substrate. All right, the first concept is inversion. So how a MOSFET controls current. So here's the concept of an electronic switch. What we'd like to do is we'd like to, by applying a voltage to the gate, we would like to allow current flow between the source and the drain, between the drain and the source, okay? And by removing that voltage, we would like to disallow flow between the drain and the source, okay? So I'm going to show you an example here. In an N-type MOSFET, the gate voltage applied, it can invert the gate region just underneath it from P to N using an electric field. And that's the magic. That's the reason why this is called a field effect transistor. So when the transistor is off, I want you to think about 3 semiconductor regions that look like this. Now, since you've studied diodes so far, I'd like someone in the class to tell me, would this allow current flow? Why or why not? So this is the gate region. Imagine the gate region is P-type. The source and drain are N-type. what does this look like? And why will it not allow current flow?
This looks like just from a top level view, a junction transistor, an NPN type of junction transistor, but
It does. Yeah, absolutely. It looks like an NPN transistor, but can you get current flow going from N to P to N?
if you don't have any voltage applied to the gate, you can't.
Can't, that's right. So why not?
If we look at the energy band diagram, you have two bins in the energy band diagram. So you won't have any sort of diffusion from the two sides.
Exactly. Yeah. So Melvin, you're actually discussing a concept that we'll talk about later. But this is what the band diagram looks like in an NPN device. You have your N region. Remember, the Fermi level is close to the conduction band. And then another N region, the Fermi level is close to the conduction band. And then you have a P region in the middle where the Fermi level is close to the valence band. So if you draw the energy band diagram for these three regions, you will see that the band diagram looks like this. We'll come back to this later, but the point that Melvin, you're pointing out right now is that there's an energy barrier that prevents electrons from going from source to drain. There's an energy barrier blocking it, okay? So that's one way to think about it. Another way to think about it is as follows. This looks like two back-to-back diodes, right? If you were to draw an equivalent circuit diagram here, whenever you have a PN interface, this is what diode looks like here, P to N, then another P to N here. So you have a diode going this way. Notice that these two diodes are oriented in opposite directions. And our intuition behind a diode is the diode only allows current flow in the direction of the arrow here, pointed by the triangle. So current cannot flow from left to right because it would be blocked by this diode. And current also can't flow from right to left because it would be blocked by this diode. So when you have two back-to-back diodes oriented in opposite directions, it effectively blocks current flow. Okay, the energy band diagram says the same thing, just in a different language. Okay. Back-to-back diodes, no current can flow. So the magic of the MOSFET is that the gate voltage can actually magically turn this P region into an N region. And we'll talk about how that happens, but that phenomena is called inversion. And the reason a field effect transistor means through a gate voltage, through an electric field, you can switch this from P-type to N-type. Okay, and then it looks like this. So what does this look like from a circuit model? It's just three resistors. There's no P to N interface, no depletion region, no diodes forming. It's just three N-type regions, which look like resistors. So this does allow current to flow between the source and the drain. Okay. Any questions here? Okay. So the question in your head probably right now is, well, this is great. So how can we switch a P-type material to an N-type material? What are the ways that we know so far? The stuff that we've talked about in class thus far. How do we switch a P-type to an N-type? Go ahead, Clayton.
Changing the doping.
Changing the doping, right. So the physical way to actually change doping involves putting the putting the semiconductor in a furnace with a process gas, and it takes several hours to do doping. So if we want to turn a switch on and off and it took several hours to do that, obviously that would not be a practical way. But the reason I asked the question is just to remind everyone, okay, so far the only tool that we have in our toolbox is to change P-type to N-type is doping, and that's super slow. So the field effect is really cool because it can allow us to change the gate material, the gate region from p-type to n-type within, within picoseconds. Incredibly fast, just by applying a voltage to the gate. And so let's see what that looks like now. So this is the structure and the physical model of an NMOS device. Okay. So the source, so it starts off with a p-type substrate. Okay. And in that p-type substrate, you have a source and a drain region. Okay. So what these regions consist of is you diffuse in an N+ region within the p-type substrate. So let me back up for a second here. You diffuse in an n-type. You can do this by a process called diffusion, selective diffusion. So you're only diffusing this region, and it dopes that. It changes the doping from p-type to n-type because you're putting in an excess of column 5 dopants here. And then you make a metal contact here. And if you have an N+ region and you put a metal on top of it, what type of contact does that form? Ohmic, Schottky barrier? Neither, both.
Ohmic.
It forms an ohmic, right? Because an N+ material will typically, depending on the metal you have, it'll either be, it'll either be an ohmic contact or it'll be like a tunneling type contact. In both cases, you have like an ohmic relationship. It allows current flow between the source and drain. Okay, so don't worry about the metal contact now. We're more concerned with the source and the drain. So the drain also is N+, highly doped N-type. And then the gate region in the middle consists of just the p-type substrate. Okay, so you have your N, the P, and the N here. On top of the gate region, there's a thin oxide layer, an insulating material that's shown in green here. That's called the gate oxide, very important part of the MOSFET. And then on top of that, there's a layer called the metal or polysilicon layer, or there's other types of conductive materials that are used here. But basically, the orange thing that you see here is called the gate, and it is a some type of conductive layer. Okay, so in the off state, the direction of current flow is going to go like this. This is the way that we want to think about current flow in a transistor, source to drain or drain to source. Okay, the current is flowing from drain to source. Just to remind you, current is flowing from drain to source, but the electrons would be moving in the opposite direction. Okay, so right now, the electrons see this depletion region here, another depletion region here, so they cannot flow from source to drain. Okay, so this device is in the off state. So now let's talk about inversion. How can we get a channel, a conductive channel, so that electrons can flow between the source and the drain? If we ask the question another way, is how do we convert the p-type material in between the source and the drain to an n-type material? How do we invert it? Turns out that these two pieces, the insulator and the metal and the gate contact, allows you to do that. So we'll see why in just a second. All right, so the story goes like this. So what you do is you apply in an NMOS device, this is an NMOS device, you apply positive voltage to the gate. Okay, VGS is greater than VT. So you're applying a voltage greater than the threshold voltage. And remember our basic model here, we've drawn this many times right now. You have a voltage source, you have like a capacitor like this. If you apply positive potential here, you get a buildup of positive charge here like this. You get a buildup of negative charge on this side, and you get an electric field pointed in this direction from the positive to the negative terminal. Okay. So that concept, again, comes up in the MOSFET. In fact, that is the basic principle of the field effect. So I know that, right now it seems like we're applying a voltage between the gate and the source, but the source is often connected to ground. So you can actually think about this, most of the time you can think about this in terms of you're applying a voltage between the gate and the substrate as well, because the source and the substrate are both connected to ground. So think about it in terms of we're applying a voltage between the gate and substrate. So when we do that, we actually have a capacitor here. This is called the MOS capacitor, MOS capacitor. Because remember, what is the structure of a capacitor? A capacitor is two metal plates. This is a metal plate. This is a metal plate. And in between them is an insulator or a dielectric material. Okay, that's exactly what we have here. The P-type substrate is a kind of a conductive material, so you can think about it as kind of being a metal. And then on top here, you have a conductive. The orange layer that you see here is a metal layer. Okay, so obviously, if we apply a voltage there, we're going to get a buildup of positive charge on the top and a buildup of negative charge on the bottom. But what's interesting is that how that happens in a semiconductor. So with the metal, of course, you end up getting a buildup of positive charge on the top region, okay? But the semiconductor substrate, what happens there is kind of interesting. So right now, the way I want to describe this to you in a sequence is that you have a buildup of positive charge on the gate, and as a result of that, you have an electric field pointing from top to bottom, okay? This is typical of any capacitor. So what does the electric field do in the semiconductor is interesting. It does two things. The first thing it does is that it pushes away the holes in the semiconductor. Remember, the P-type substrate has holes and electrons. Holes are the majority carrier, so there's lots of holes. And then there's also minority electrons. Okay. So this electric field does two things to the hole. The first thing it does is it pushes the holes away. Holes move in the same direction as the electric field. So you can imagine that the holes in this region, this is where the electric field is strongest, just underneath the gate oxide, holes get pushed away from there. And the electrons, what happens to the electrons? Someone in the class.
They get pulled up.
They get pulled up. That's right. So this process of holes getting pushed away, that is called depletion, because we are depleting the channel region underneath the gate oxide. We're depleting it of holes. We're depleting it out of the majority carrier. So that's why that process is called depletion. As Clayton said, the second effect that happens is when electrons get pulled in here. So you can see the electrons, because of the electric field, they get pulled in to a region just underneath the gate. That process is called inversion. Okay, so how the process works is like at low voltages, if you just apply a small gate voltage, you'll start getting some of these depletion effects. But the inversion effect happens only when the gate voltage exceeds the threshold voltage. So you have to apply a voltage that's large enough in order to get the inversion effect. Why? Because there aren't that many electrons in the P-type substrate. Remember, there's tons of holes, but very few electrons. So this inversion effect only happens at sufficiently high gate voltage. But when this happens, it's super interesting, is that you end up getting an N-type material underneath the channel. You see? Just think back to what our definition of semiconductors is. A P-type material has lots of holes and very few electrons. An N-type material is lots of electrons, very few holes. So the field effect is essentially switching this from P-type to N-type just in that region where there's a strong electric field going through there. It inverts the material from P-type to N-type. Very, very interesting effect. And bam, this is how you have your electronic switch. Just by applying a gate voltage, you've switched the semiconductor just in this narrow channel here, the inversion channel. You switched it from P-type to N-type, and now you can have nice current flow going from the electrons can flow from the source to the drain And he can even go in the opposite direction too. Any questions? So this is the process of inversion. All right, now we're going to get into, this is the main concept here. This is how you turn the transistor on. But remember, turning it on is not enough. You also, if you want to get current to flow between the drain and the source, or source to drain, you have to apply a voltage. And the way that we said an NMOS device works is that you apply a source to gate voltage, gate to source voltage, sorry, to turn the device on. And then you also apply a drain to source voltage so that you can get current flow from drain to source. So remember, current flow from drain to source means the electrons are moving in the opposite direction, like so. Okay, so this is what the device looks like in the triode region. You apply a gate to source voltage and you apply a drain to source voltage. But that VDS is on the smaller side of things. Small drain to source voltage. Okay. So we know current's flowing between the drain and the source. This is always a tricky question, but I always like to ask it anyways to see what students can come up with. Why do you think the way I've drawn this channel here is that I've drawn that the on this side of the channel you have a thicker channel. It's not physically thicker, but there's a lot of electrons. This is very n-type on this side. It's less n-type on the other side. Can anyone think of why? Why would applying a voltage between the drain and the source cause the right side to become less n-type than the left side? This is actually a pretty tricky question.
I don't really know what it is, but does it have something to do with the voltages, given that the source is typically is in this case ground, and the drain is kind of has a voltage on it?
Yeah, it has to do with the voltages on the drain side versus the source side. Absolutely. So you're in the right direction. You're in the right direction. So I guess let's just use that as a segue to get into this discussion then. So yeah, current's flowing this way. Now I want to start by reminding you of a kind of a more fundamental concept in electromagnetics, and that is the voltage drop across a resistor. Okay, so imagine you have this situation. This is your voltage source here. This is your positive side and this is your negative side. So you have a current flow. The current is flowing this way and it's flowing this way through the resistor. Okay. Now with Ohm's law, I know you all remember Ohm's law, V equals IR. So that tells you the current I, the voltage drop across the resistor, across the entire resistor from left to right, and the resistance here R. Now what you may not know about Ohm's law is that the voltage within the resistor, if the resistor has a constant cross section, then the voltage will drop gradually as you go from the positive end to the negative end. Okay, so let me just draw this. So this side, this wire is obviously 10 volts. Okay, so this side of the resistor is 10 volts. When you get here, the voltage within the resistor drops to 9 volts, and then 8, 7, 6, 5, 4, 3, 2, 1, and then finally 0. The voltage is dropping as we go from one side of the resistor to the other. Okay. And one intuitive way that you can think about this is you can think about this resistor as being a bunch of smaller resistors connected in series with each other. Okay, so again, Ohm's law, V equals IR. So there's going to be some voltage drop. Let's say there's 1 volt across here, another 1 volt across this resistor. So a bunch of these resistors in series with each other. So the voltage here starts off at 10 volts. So you have a 1 volt drop across here. So the voltage at this node is 9 volts. Another 1 volt drop across here. So the voltage at this node is 8 volts, and so on. The same current is going through there. The same current is going through all the resistors, but there's a voltage drop across each resistor. Okay. The main point, again, is that the voltage inside a resistor drops linearly as you go from one side to the other. So when we revisit this diagram, we can look at the voltage in the NMOS channel. Here we were looking at the voltage inside the resistor as we were going from this side to this side. Now we are going to look at the voltage in the inversion channel that we just talked about. All right. So if we compare the left side to the right side, on the left side, we have a lower channel voltage. Let me explain what I mean by the channel voltage. The channel voltage is the channel in this part, in this blue region, within the inversion channel. Okay? So just like the resistor, within the resistor, the voltage drops as you go from the high side to the low side. Here, the channel voltage is going to drop as you go from the right side to the left side. Okay? But this does something to the electric field. Okay, imagine that we put a voltage VDS, okay, or just call it VD, okay? On the right side, on this portion of the channel, the voltage, the channel voltage is high. And on this side of the channel voltage is low. So what does that mean in terms of how inverted the different portions of the channel are? Okay, so the way that we kind of think about this is that we're thinking about the channel as an MOS capacitor. So this is the gate, and this is the channel. Okay. So the gate is connected to a metal side. Okay, the voltage here is the same everywhere. We can call that V gate. But the channel side, as we just showed here, the channel voltage is changing as you go from one side to the other. So one way you can kind of think about this is how inverted is the channel? How inverted is the channel? One way we can think about that is the basic capacitor relationship Q equals CV. All right, the charge, okay, we would like to have a lot of positive charge on one end and a lot of negative charge on the other end, because negative charge means the channel has become N-type. So we want lots of charge. Charge is equal to the capacitance times the voltage difference between the top and the bottom. So this is the capacitance times the gate voltage minus the channel voltage. All right. So what I want you to see is on the right side of the diagram, the channel voltage is high right? So the channel voltage is high, so that's going to result in a smaller Q, a less inverted channel. On the left side, the channel voltage is low, and so that's going to result in maximum Q for the most inverted channel. Okay, so that's why we draw the channel kind of in this triangle shape to denote the fact that the channel is actually very conductive on the left side, most conductive on the left side, and actually less conductive on the other side. At the extreme case, you could have a situation where there's hardly any charge at all on the right side. Okay, that's if the channel voltage is very large. If you apply a large VDS, you're going to have a very large channel voltage here, and that's going to result in a very small Q. And it can get to the point where if it's larger than, when VDS is greater than VGS minus VT, that part of the channel can become pinched, and that is the different mode of the MOSFET. That's called the saturation region of operation. Okay, so that's what we're looking at here. If the drain to source voltage exceeds VGS minus VT, then you'll be in this situation where the right side, the channel voltage on the right side is too large, is large, so you end up getting your Q on this side could end up being 0. That means you have no inversion, your channel is pinched off there. And so then you draw the channel like this to show that there's no inversion channel here. Or there's a very narrow, it's kind of like pinching a garden hose. Okay. So as a result of this interesting phenomena, this pinch-off effect, you end up with this unique IV characteristic that I showed you earlier, where the channel current changes only slightly or not at all as VDS is increased. That pinch-off effect results in this portion of the IV characteristic, where the ID is relatively flat compared to when plotted against VDS. Okay, that's the physical origin of the saturation mode of operation. Okay. So in this last 15 minutes of class here, we're probably going to take an extra 5 minutes today, so we got started late. So we're going to take a look at the IV characteristics of the two common modes used in MOSFETs, the triode region and the saturation region. So I described to you qualitatively how this worked, well, semi-quantitatively, but now we're going to go and actually derive the equations. Okay. So in order to derive the transistor currents in each of the regions, the triode region and the saturation region, we have to go back to some of the basic relations of conduction. And we can talk about conductivity, which we learned in Module 3. The conductivity is equal to mobility times the volumetric charge density. Okay, and remember the key concept here is electricity is moving charge. So how conductive a material is, in other words, how well it conducts electricity, has to do with how many charges you have, Q, and how fast those charges move, which is mu, mobility, in response to an electric field. Okay, so that's our relationship for conductivity. And then the current is given by Ohm's law. And, of course, the V equals IR is the most common form of Ohm's law, but we can do I equals 1 over R times V, which is the conductance times V. Okay, and so that's where this mu times Q comes from. So we're going to derive the current in the triode region here by just revisiting this diagram in a little bit more detail. So first of all, recall that there's a mobile charge on the inversion channel that's due to the minority electrons. The charge density depends on the location of the channel, so the conductivity will vary as well. This side of the channel is going to be very conductive, and the right side of the channel is going to be less conductive. So if we know the charge density and applied voltage, we can calculate the current. That's the derivation that we're going to do. This dimension that we added here, x, that is our positional dimension. So what we're going to find is that the resistance of the channel, we're going to break this channel up into a bunch of series resistances, as I showed you a few slides earlier. And we're going to find that this is going to have the least resistance, this is going to have the most resistance. And so we have to find a composite resistance for the entire channel. Okay, so we know that the channel voltage looks like this. This is something we've already looked at here. The charge is going to be C times V. The basic relationship for charge on a capacitor is Q equals CV. So as I said before, this is going to be C times V of the gate minus V of the channel. Okay, and the difference in the equation that you see here is that you have this added term VT. Okay, that's something I didn't include at the beginning there, but that this term should be here too, because whether you have inversion or not, you have to exceed the threshold voltage by a certain amount. So that's why this VT term is there as well. Okay. So the amount of charge is going to be largest on the left side and smallest on the right side. So this is a quick derivation of the current in the triode region. Again, we have the picture here. And the intuition that I want you to think about is that this inversion channel is going to be broken up into smaller pieces. Okay, so you can imagine breaking that up into smaller blocks here. And each of these little blocks is a resistance. So this one long channel can actually be thought of as a bunch of series resistances. And that's how we're going to go about this derivation. Each of these little regions has a width dx, what we call a differential width. All right, so we're going to start off with Ohm's law. ID is equal to sigma times V. Conductance times the voltage. As we saw before, the conductance is equal to mu times Q, mobility times charge density. And then we can take this and bring this into a differential equation. So this is the key trick here. We broke it up into small pieces. And now for each of these pieces, we are assigning a differential equation which describes the current voltage relationship in each one of those little blocks. And so you can see this is the mobility of electrons, mu n. The width here, this has to do with the geometry of the device. Okay, because we want to find the total charge. So we have to multiply the charge density by a geometric factor. A Qn of x, this is the charge density as a function of x. So this is the intuition here, is that, remember, we have a lot of charges on this side, fewer charges on the right side. And then dV dx is the voltage across this, the voltage drop across this resistor. That's the dV dx there. So that's kind of the intuition part. That's the engineering part of things. The rest is just math. And we're obviously not going to focus too much on the math here, but I want you to see a little bit of the tricks that are used. You take the dx and you put it on the left side first. So now you have an equation, I dx is equal to mu nw qn dvx. This has a dx in it. So the left side has a dx in it. The right has a dvx in it. So one mathematical trick is that you can actually integrate, in a differential equation, if you have two different variables on both sides of the equation, you can actually integrate the left side and the right side with respect to different variables, and it'll still be valid. So we integrate the left side of the equation with respect to x, and we integrate the right side of the equation with respect to voltage. Now, in order for this trick to work, you have to have some correspondences between the x variable and the voltage variable. So so if we're integrating from the left side of the channel to the right side of the channel, so we're trying to incorporate all these little resistance blocks here, we're integrating from one side to the other. So in terms of the variable x will be integrated from x equals 0 to x equals L. L is the length of the channel. Okay, so this here, this is x equals L. This here is x equals 0. So we're integrating from the left to the right side. So the limits of integration is x equals 0 to L. In terms of voltages, we know that as we go from the left side of the channel to the right side of the channel, this side is going to be 0 volts. And the right side of the channel is VDS, whatever drain to source voltage we applied to it. So we have our limits of integration in terms of voltage as well. Okay, so that's one of the key mathematical tricks. We can substitute a value for Qn. Remember, Qn is equal to Ci times Vg minus Vt minus Vx. So that's where these new terms came from here. And then when we finish the integration, the voltage here is voltage is varying as a function of position. Okay, this is a constant here. This is a constant here. This is the only variable that changes as a function of x. So when you take this is really the only variable that we're integrating. And when you integrate a linear function, when you integrate the function x, you get x squared, right? So when you integrate this Vx function, you end up getting a parabolic function, a squared function. And so that's where this term comes from. Okay, when you do the definite integral, this VDS is your VD term here. And so that's where that squared term comes from. So you have a linear term and a square term here, both. Okay, so this equation describes the current in the triode region. Now, one little thing about this is that if you look at the IV characteristic of a diode, I'm just going to draw it here again, VDS and then ID. I mentioned to you is that the current voltage characteristic looks something like this. Okay, this part here, you can see that this looks very much like a straight line. This is resembling a straight line. Why is that? And then why does this part look like this? So this is, I'm going to say, this is the linear region. This is where the current voltage characteristic is linear. And then this region here is where the current voltage characteristics looks more like an inverse parabola. So this is where that squared term becomes significant. And then everything out here, we're not talking about this yet, but this is a saturation mode, saturation region. Okay, but let's talk about where this comes from then. This is the equation for the diode. I'm sorry, the equation for the MOSFET. Okay, notice you have two terms here. You have this term that depends on VD, and then you have VD squared. Okay, so that is the x-axis here. VDS and VD, you can think about them as being equivalent. So for small values of VD, this squared term actually turns out to be less significant. This term becomes more significant, so you end up getting a linear IV characteristic. As VD goes up, all these rest of these terms are constants, so the I is a linear function of VD. At larger values of VD, this squared term takes over, and this first term in the brackets goes away, and you end up having something that looks kind of like an inverse parabola. You can see that this is a function of negative VD squared, so that would be an upside down parabola, and that's why you see this curve here. Okay, but when you're in the linear portion at small values of VD, That is called the linear section. And this, as I mentioned, this VD squared term goes away. And you're left with just this first term here. And if you want to find the equivalent resistance, the slope of the line determines the resistance. You can derive the resistance this way. This is just by looking at the slope of the line. So 1 over R equals mu n W over L Ci Vg minus Vt. W is the width, L is the length of the channel. Ci is something called the unit capacitance, which you'll see that when we do an example problem there. Vg minus Vt, the gate voltage minus the threshold voltage. So here, from a circuit designer standpoint, you can say like, well, this equation will help me find the resistance of the channel here. And then finally, the current in the saturation region, this is what occurs when VDS is greater than VGS minus VT. This is where the pinch-off effect occurs. And if we look back at this graph here, we said that the saturation region occurs when VDS is greater than VGS minus VT. Triode occurs when VDS is less than VGS minus VT. So the boundary between the two regions is when VDS is equal to VGS minus VT. That's what this dotted line represents here. Okay. So the way you want to think about this algorithmically in your head is that if VDS is greater than VGS minus VT, you have to have the saturation region equation, and then VDS is less than VGS minus VT, just use the triode equation. So right now we're talking about the saturation equation. Okay, this and one more slide will be done. So the onset of saturation occurs at VDS equals VGS minus VT. And this value of VDS is defined as VD sat, the saturation voltage. So the way that we can find the current in the saturation region, at least the first order model of it, is we use the triode equation and we plug in a value for VD is equal to VGS minus VT. And then this is what we'd end up getting. Remember, at larger values of VD, this first term goes away. So this is the term that becomes significant. So if you remove this term here and you plug in VGS minus VT for the second term, then you will end up getting the saturation current equation. 1/2 mu n Ci W over L Vg minus Vt squared. Okay. So I have an important point here. This is ignoring channel length modulation. Okay, the way that I've structured this module here is that we talk about channel length modulation later on. And so right now I'm just giving you the very basic equation for the ideal behavior in the saturation region. Ideal behavior means the IV characteristics look like this, where this line is completely flat. Okay, we'll find out later, due to something called the early effect, that our short channel modulation is that there's actually a bit of a slope here. But we'll get to that a little bit later. Okay, so we covered the current in the saturation region. I talked about the PMOS and NMOS IV characteristic. This is what an enhancement mode NMOS device looks like. An enhancement mode PMOS device looks like you take this IV characteristic and you reflect it across the origin. And that's what the IV characteristic would look like here. The way the structures are different is, this is an NMOS device that we've spent a lot of time on. You have an N-type source and drain, P-type substrate. You apply a positive potential on the gate to source, and you also apply a positive voltage between the drain and the source. In the PMOS device, it's the opposite. The source and drain are both P-type materials. The substrate is N-type. And so the inversion that happens is that you actually are creating an N-type channel. I'm sorry, you're creating a p-type channel between the source and the drain to connect the two p-type regions together. Okay, in a PMOS device, you actually have to apply a negative gate potential in order to attract the minority holes up below this channel region and push out the majority electrons. To do the inversion, you basically have to apply the opposite polarity of voltage. That's why I told you that the PMOS device is essentially the converse or the complement of the NMOS device. And that's why you see all these IV curves are basically the inverse. They're reflected over the origin because you apply a negative gate voltage. You see the negative gate voltages here. And you also apply a negative drain voltage as well. The current flows from source to drain. The holes are flowing in this direction. Okay, and that's why your curves look like this. So I want you to think about this in more detail on your own. So these are the questions that I'd like you to think about. What is the majority carrier in the channel during inversion in a PMOS device? What direction is the electric field during inversion? What direction does current flow in a PMOS device? So if you can answer those questions for both the NMOS and PMOS device and know the differences between them, then you'll have a good understanding. Then the final concept here before we end class here is that there are enhancement and depletion mode devices. And we'll touch on this again at the beginning of next lecture here, but basically depletion mode devices are devices that are normally on. Enhancement mode devices are devices that are normally off. So what does that actually mean? If we look at the classic NMOS example, I basically said that in order for you to get a conductive channel between the source and the drain, you have to apply this gate voltage. You must apply that gate voltage. If you don't, then there's no conduction there's no conductive channel between the source and the drain. Okay, so that's what's called a normally off device. If you don't do anything, the device is off. And that is an enhancement mode device. A depletion mode device would be a device that's normally on, where if you don't do anything, if you don't apply any gate voltage, there's already a conductive channel. And you can actually apply a voltage to it to get rid of the conductive channel. Okay, so you can play those kinds of games too. I haven't talked much about how you could do that, so we'll get into more of the details of that when we talk about energy band diagrams. But there is a way to do that, to have a normally on device, and that is a depletion mode device. When you have a depletion mode device, the threshold voltage is actually negative. So that when you apply 0 volts is applying nothing at all, you still have a conductive channel. Okay, so this table summarizes all of them: enhancement mode device, positive threshold, depletion mode NMOS device, negative threshold. In both cases, you apply a positive VGS, the current flows from drain to source. In a PMOS device, things are opposite. In an enhancement mode device, the threshold voltage is negative. In a depletion mode, PMOS, the threshold voltage is positive. And then in both the cases, you apply a positive source to gate voltage, not gate to source, and current flows from the source to the drain. Okay, we'll end here. This will be one of your questions for your homeworks. Maybe we'll, if you'd like, you can go do these calculations on your own. You should be able to do them now. See what you struggle with. We can start next time in class going over these questions. And next time in class, we will also talk about the band diagrams and equilibrium and so on. So we'll get into the energy band model of the MOSFET device. Okay, good. So we got through a lot of the material that I wanted to get through today. Any questions before we end class today? No questions? Okay, great. Thanks for your attention. Thanks for staying a few minutes later. And again, great job on the test. You all did a wonderful job on the second exam. And I hope to see a repeat of that on the final exam. So, okay, everyone, I'll see you on Wednesday. Actually, I'm going to stop the recording here. And then we can stay, if anyone would like to stay extra for going over any of the test questions, we can do that.